It's you will not be asked to work a complete polyprotic acid. I will work one through for you, but I do want you to be aware of what goes on with them. It falls into the category of mixtures. So basically, polyprotic acids have multiple protons. Here we have a Ka1, Ka2, Ka3, just like I told you to do before. If you'll notice, these are the ones that interact. So those are the ones that cancel out. So if you're going to solve for a Kb3, you need a Ka1. Kb1, you'll need a Ka3 because they're one step and they affect the equilibrium. So as you're looking at the Ka1 versus the Kb3, they'll cancel out just like I showed you previously. So you have to have the values that cancel out. So as you look at these, the Ka3, the Ka2, whoops, I got ahead of myself here. Ka2 will dissociate into H plus Ha2 minus. Now, my recommendation is work through this. This is right here again. Remember, the bases start with the fully deprotonated and the acids with the fully protonated. And you can look at these and work through them. So, again, my recommendation is you finish this out so you have the information there. Now, what do you do with a polyprotic acid when you solve it? Well, we have several things going on here. First thing is you're going to lose one proton at a time. So when you do that, the first equilibrium is going to affect the second equilibrium, is going to affect the third equilibrium. If you had 4 or 5, then that would continue on. So much like the common ion effect in KSPs, you're going to have an issue with the protons from the first step impacting the second step. Now, something else you'll see here is, wait, the pKa's are listed here. Well, the smaller the pKa, the stronger the acid. You know, wait, what? Remember we said we could take a negative log of anything, so we could take that. Now, this is really how, if you're looking up a table of weak acids, that you're going to find it, because it's easier to list it this way. So, for example, for the first one, Ka1, it's going to be 10 to the negative 2.14. So, Ka1 will be equal to 0.007244436. Ka2 will end up with 6.16595 times 10 to the minus 5th. And the Ka3 is 1.698244 times 10 to the minus 10th. Now, if you notice looking at this, the first Ka is pretty strong because it's minus 3. The second Ka is okay, it's minus 5. Then the last one is minus 10. That's not a 6. So what happens is it's getting weaker as you go. Now, we're going to call this, since this is a triprotic acid, we're going to call this H3A. So let's work a problem. I obviously don't have enough space, so I'm going to add a page onto this. So what we're going to do is set it up. So first things first, we're going to do the first proton. And it's H3A. Is going to dissociate into H plus H2A minus. It's an ICE table. So we started with the concentration of 0.025. So it's 0 and 0 minus X plus X plus X, 0.025 minus X, X and X. So the Ka1 is going to be equal to the H plus times the H2A minus over the H3A. So if you're looking at this, you're like, wait, we've already done this. Yep, it's going to be X times x divided by 0.025 minus x is equal to your Ka1, which we found as 0.007244436. So we end up with x squared plus 0.000724436x minus 1.81109 times 10 to the minus 4th is equal to 0. So we get our x value is equal to 0.01031443, which is our H plus concentration here and is also equal to our H2A concentration. Now, if we just add a sheer entertainment value, try to figure out what our percent ionization is. Our percent ionization for this species is 41.26%. So that's actually pretty good. So it's a relatively strong acid. Are we going to do anything with that? No. I'm just going to throw it out there. Now I'm going to change colors so that you can see the difference. Here's our second proton. We're going to start with H2A minus is going to dissociate into H plus HA2 minus. We're going to do our ICE table. Now here's where the fun begins. And by fun, I mean not really. If we're looking at it, this value here has to come down here, which we found that value as 0.01031443. Okay, so wait a minute. This comes down here. So this one is 0.01031443. This one, the last one, which we don't have anything, is 0. So what did we just do? We found the reactant, but we also had a product. Now Le Chatelet's principle comes into play. So are you thinking it's going to dissociate as much as an A or less? Well, according to Le Chatelet's principle, we have some product. It's the common ion effect. So therefore, it's not going to dissociate as much. But we still have a 0 on the product side. So we have to get something there. So 0.03143 minus x, 0.010314443 plus x, and then this one comes out to be x. So again, this is our Ka2. So it's going to be equal to 0.01031443 plus x times x divided by 0.01031443 minus x is equal to my Ka2. Well, my Ka2 is 6.16595 times 10 to the minus 5th. Now, we had a high dissociation before. According to Le Chatelet's principle, we're going to retard the dissociation, and our K value is small, so we're going to assume dissociation is minimal. Now, when we do that, we always have to check, but that makes our Ka drop to 0.01031443 divided by 0.01031443 with the x up at the top. So wait a minute, these two cancel. So basically my x is going to be equal to 1.6595 times 10 to the minus 5th. Anytime you assume, you must check. So my check is my percentage, which would be the HA minus concentration over my H2A concentration times 100. So that's going to be equal to 6.16595 times 10 to the minus 5th divided by 0.01031443 times 100. So our percentage is going to be equal to 0.597, 0.59. 0.78%. So it is less than 5%. We are good. And it is. So here's my check, and I can make that assumption. Okay, so let's move on to the third proton. Well, it'd help if I could draw a third proton. Well, here we're going to start with Ha2 minus is going to dissociate into H plus A3 minus. And we're going to get our value from here. We'll go in here. So we have a whopping value of 6, this is my ICE, 6.16595 times 10 to the minus fifth. Now, my H plus is actually going to be this value here, which is the 0.0103141 plus 6.16595 times 10 to the minus fifth. So what that actually gives us, if when you add it together, is 0.0103761. So it's slightly higher than what it was before because we have to have added it in, and this is our 0. So we're going to lose x, gain x, and gain x. So it's 6.16595 times 10 to the minus fifth minus x and 0.0103761 plus x and then x. So our K A3 is going to be equal to 0.0103761 plus x times x divided by 6.16595 times 10 to the minus fifth. And our K value is 1.698244 times 10 to the minus 10th. Okay, so if the assumption worked before and we've just added more, our equilibrium value is less. So first off, we don't want to dissociate. You've dumped a lot of common ion in there, so it's going to stop it. So we're going to assume, again, that dissociation is minimal. It was so small before, and it's going to be less. So we're going to get 1.698244 times 10 to the minus 10th is going to be equal to 0.0103761 divided by 6.16595 times 10 to the minus fifth. And I forgot my x up here. So your x is going to come out to be equal to a whopping 1.0091748 times 10 to the minus 12th. So we're going to check it over here in our corner. So that's going to be 1.0091748 times 10 to the minus 12th divided by 6.16595 times 10 to the minus fifth times 100, which comes out to be a whopping 1.63, if I can read my writing, 6362 times 10 to the negative 6%. Excuse me. So my assumption is valid. So we made our assumption and we're good to go. So wait a minute. I forgot what the question was. It says, what is the pH and concentration of all species present in the final solution? Okay. Well, I'm going to come back over here just because final values. So if I look at it, if I go back, my H3A, which we would have to subtract, is 0.0146856 molar. My H2A concentration is 0.010257 molar. My HA2 minus concentration is equal to 6.16595 times 10 to the minus fifth. Okay, real quick, what I'm actually doing is doing these values here. So I'm subtracting or adding, well, in this case, subtracting where I need to. And so my A3 minus concentration was my final one, which was 1.00917 times 10 to the minus 12th. Now, my H plus concentration got added to each time. So my final H plus concentration was 0.010376 molar. So if you go back and you look here, we added this in here. And then here we would add this value again, which is really small, so it's not going to contribute. So if that's the case, the pH then is equal to 1.98. Now, we don't do a pH for each step because they're all in the same solution. So we have to wait until the end to do our pH. And then we wanted the percent ionization, which we did as our check. So the percent ionization of the fully deprotonated was 1.6362 times 10 to the minus 6. Now, you can also do the percent ionization of the fully deprotonated by doing the A3 minus concentration over the formal concentration initially and times 100. And if you do that, you get 1.00917 times 10 to the minus 12th divided by, what was my concentration? 0.025 times 100. And this is one way to do this percent ionization. I tend to do it regular, but some people like to do the whole thing. 0.025 times 100. So this one's actually worse. You end up with 4.0367 times 10. That's a 7. Times 10 to the minus 9th percent. So if you're looking at this, the percent ionization of polyprotics, basically the pH is the first step, because after that Le Chatelet's principle kicks in and you stop generating much H plus because of the fact that you keep adding H plus in. So this will most likely appear on the test in multiple choice or just generic questions about it, but I will not have you work a full problem.